you to be cautious. Because so far in this module, we have basically discussed a lot of types of stability and we have two stability. One is something we covered before this week. That stability is whether your signal is stable, whether your difference equation is stable. That one is only talk about the signal itself. Only talk about the representation of the signal by a function itself. Has nothing to do with your transfer function, has nothing to do with your input-output. Okay? So for example, this one. This one, after you have done the Z transform, you get the Z function. Right? You have conclusion where this one will be stable or not stable. And this stable means what? This stable means your signal, whether the signal is stable, means when your time, when your k go to infinite, whether your value will be infinite, whether your value will be counted. So actually the conclusion is obviously for the exponential function to be stable, your k must be less than 1. If your k is bigger than 1, sorry, if your r must be less than 1. If your r bigger than 1, your exponential function will diverge to unstable. Right? So for this one, we only talk about the signal itself. So for this one, you can do a simple check, find out where the root it is. In the T domain, if all the roots, if all your poles are inside the unit circle, your system is stable. And this stable is only talk about the signal or the transfer function or the difference equation themselves, and nothing to do with your input-output response. So similar for this one. This one is just a difference equation. The difference equation represent a certain data, right? And the signal is only represented whenever you have first unit and you have initial condition, then so on. It never be judged by any other input function at all, right? So for all the things we have talked about so far, is only about the stability, about the transfer function themselves, about the signals themselves. So sometimes we also can call as the internal stability, because this one has no relationship between other signal and no relationship between signal and transfer function and output. So if we look at the trapezoidal function itself, the transfer function itself is known as your Z. This one is marginally stable. It's not as stable, it's marginally stable because your root is 1. Is a non-unit circle. Right? So the trapezoidal signal itself is marginally stable if you look at the root. But if now we look at the PIBO, which is different from your internal stability. Internal stability only look at the signal, only look at the transfer function themselves. There is no interaction at all. Okay? And this one you can be determined by look at the root, where the root impacts it is. And if all the roots are inside the unit circle, is internal stability. But the PIBO means the external, it means your transfer function, your system have something to do with your input. So we are looking at the stability as a systematic point of view. You have a bounded input and want to see whether your output is bounded. Then we examine your transfer function, your controller, your system whether stable or not stable. So this stability depends on your input-output response. So as long as your input is bounded, your output should be bounded. Okay? So if the PIBO does exist, as long as you give any format of your input, it can be a unit step, it can be a cosine sign, it can be a decade exponential function, or combination of all of them. It also can be some random value. You can have a random input. T0 equal to 1, T2 equal to 3, T10 equal to 100, T4 equal to -10, as long as all your random value is bounded by a range. Then your output will also be bounded. So your PIBO is talking about the external stability is something dealing between your input-output stream function. And the condition for your PIBO will be also much different, which we need to be tested by the in-house response. And it's not going to see when your time go to infinite, whether your in-house response is still finite. Not only that. is the summation of all your impulse response at any time movement from negative infinite to the positive. You must sum up everything. So just now the trapezoidal. If you do the impulse response, what is the response? You will be half t, t forever. Your t is a fixed period. So your impulse response of the trapezoidal itself is bounded, is finite, is converged with t. But the trapezoidal itself is not VIBO stable. Because if you sum up all the response, you sum up all the t, you sum up all together go to infinite. You have infinite time, right? Then you become t multiplied with infinite. Then it's infinite. Then it's not bounded. So I want to use the trapezoidal function to be a caution to see how you actually examine the VIBO. It's not looking at the roots. The root is for the internal stability. But your internal stability does not guarantee your external stability. Because later you may have other type of input coming which is bounded. But your system eventually is not bounded. So by we do the testing by the impulse response. But be careful, it's not just an impulse response itself. It's not a single value, it's not the final value. It's all the values sum up. So you must pay attention to this thing. It's not to say this one is infinite, it's the summation of the infinite hk to be bounded. So this is the testing. Okay? So we will go through this testing by a simple example as this one. This one we want to see whether this one is stable or not. First of all, you notice this is something different from our previous example. In our exercise, we have similar question. We have a1 uk minus 1 plus b1 or a1 uk minus 2, right? This is something we had previously in exercise. Now the difference, only difference now is that the uk minus 2 we have uk minus 1. Uk means what? Uk means what? So this one now is actually a transfer function. Because this one dealing with both your input and your output. Is that right? This one dealing with both your input and output. So now for this one, how can we do? If we do the impulse response, what do we get? Let's do a very simple table. We have a K, we have a UK, we have a UK minus 1, we have a UK. So when if K is equal to 0, what do we get? My input will be 1, right? Because the EK, the definition is the impulse is when your K equal to 0 is what? The others 0. So only at time 0, I get the input which is 1. So this one is 1, so UK minus 1 previously, U minus 1 is 0, right? Then how much is my UK? My UK is equal to A1 UK minus 1 plus B1 EK, right? So now my EK is 1, so what did I get? Okay. B1 times 1, right? So B1. Is that right? When my K is equal to 0. So when my K equal to 1, what I get? My input system becomes 0. How much is my U1 now? My U1 is this one, right? U1. So how much is my U1? U1 minus 1 is U0. U0 is U1, right? Yeah. So how much is my UP now? My UP will be updated by A1 multiplied with UK minus 1, which is A1 U1 plus B1 times 0. Right? So it's just A1 times B1. When I give up the 2 what I get, my input is 0. Then my UK minus 1 become my previous UK, right? So because my time shift, this is my UK minus 1, so how much is my output? A1 times A1 B1, which is A1 squared. So when my time go to 3, so what it is? A1 cubic B1. So if I come to n, what I get? Maybe a n minus 1, e1. Okay. So how should we do? And now actually your hk is the same, your uk is the same as your hk, right? Correct. Because it was response. So if I want to do my summation from a to infinite, finite of my hk, what I get is my summation of my ak k1 of k d1. So what it is? d1 is a constant, right? And this one I do hope all of you shall get familiar with the summation of a very simple infinite power series, right? So infinite power series is when a1 is less than 1, this one will become e1 1 over 1 minus.
这是infinite 啊，这是
Then this one is so-called bounded.
卡不懂。
Because this is the final value, right? But if your a1 is greater than 1, greater or equal to 1, will be unbounded. So what's the condition for the system to be stable? Your a1 must be less than 1. I mean the magnitude value, right? If your a1 magnitude value is equal or greater than 1, the summation will be unbounded. Even this one is equal to 1, then what you have? Infinite, right? You have infinite summation. Any questions?
Yes.
your stability is depending on the A. Stability depends on A. Okay, so basically we spend about 1/2 hour about the unit pulse. So unit pulse is a very important function. It's a very important signal because this input signal can help us to link between the transfer function and the output response. And also this one can be a good tool for us to evaluate and check the bounded input and bounded output stability. Okay? So we give the impulse response. We sum up all the impulse response. If the one still converge, then your system is stable. Okay? Okay, so besides the unit pulse, in the general input, we will have something unit step. So we should also know how to represent the unit step into the Z domain. So the unit step, how to do the Z domain, you put down the definition
last warning.
of the Z transport. So because this one starts from 0, so you can simplify from 0 to infinite. Okay, and see power and escape. And this one is a very simple infinite power series. Okay, so it's 1 over Z. Okay, 1 over Z power minus 1. Okay, 1 over Z minus 1 over 1 minus Z power minus 1. This is here to here is because the infinite power series. Okay, which I think is very complex. So for this one, you see this one have a 0 and 0 and the pole at 1.
Small into a pole.
into a pole and Z equals
Okay, in
S
the
is
display.
zero 什么？
to 0
我也不懂啊。
有拍照有
You
拍
also
照
see
拍
the
照
explanation, right? If you do the explanation function to do the Z transform, what do you get? You will get Z divided by Z minus R. So basically, they are infinite power series. Just for this one, the power is Z power minus 1. And here is R multiplied with Z power minus 1. This is a little difference. And here you have a pole which is at R. Okay? You have a pole which is R. So for this one, if you want this one to work to be stable, it means your explanation function must be converged, your R must be less than 1. Right? Your magnitude of R must be less than 1. And for the unit step, you see this one that never go diverse, but also never take it out, right? So you see this one has a pole at 1. And if you want, you can also express some general single functions. And because the sine and cosine function can be expressed as an exponential function, right? In the imaginary part. Okay? So this is how you can convert your general sine and cosine functions into certain exponential functions. After you can come to the exponential function, you are also able to utilize the infinite power series to find out the total summation. Okay, but of course here you have to maintain. And this is how you can represent your sine and cosine. Okay, actually for this one is a cosine. Okay, this one is a cosine symptom. Okay, so for the Z transform you see is a second order. You have a root okay, at R plus minus cosine theta. And actually, you can consider most of the functions as a special case of the general cosine cycle. So if your theta is 0, then your equation will become exponential function.
Irritating.
If your theta is 0 and your r is equal to 1, your exponential function can be even simplified as your unit step. Okay, so similarly, I think this is something quite similar as your integral domain. Then you represent your unit step, you represent your z, then you represent the cosine sine, your exponential function, right? You also get all this starting s function, right? They are also get all this starting s function. So similarly, for all the digital discrete signals input, it can be transformed into a certain step function. If you know the mathematics, okay, if you know the mathematics function. And if you want to remember, you will remember this one, you will remember everything. Actually very simple, you see if your theta is 1, what it is? Z minus R divided by Z minus R squared. You answer 1, Z minus R, what you get? Get this.
John.
If your I equal to 1, what do you get? Get this. So your unit step can be considered as a special case exponential function where your base is 1, where your r is 1. Your exponential function can be considered as a special case of a cosine sine function. Okay? It's just the imaginary part is 0. You only have the real part. So now, up to today, I think finally, you can complete the whole cycle to convert and link your transient response in the digital domain. Right? So what do we mean here? Now, let's review this step again. I think we have reviewed this one in the continuous domain review for week 1. Right, week 2, week 3, we have explained how to prioritize it, right? By the continuous one, now, after we are able to find solve the continuous exponential response. So now what the real axis means? The real axis of this part means exponential function. What this point means? Unit step. Right? R equal to what? Theta equal to 0. For the rest, make the theta equal to 0, if your theta equal to 0. This one is just for exponential functions. Okay? And if your theta is not 0, okay, be careful. Theta equal to 0 only means this one is theta equal to 0. This one is what? Theta equal to pi. Okay? If here theta is not 0, theta equal to pi, right? So what this one means is a general cosine sine function. And what is? It's a 90-degree sine function. Give it here, cosine function. Okay? So now you should have another view about this graph. Because your signal, depending on where you look at this, because basically this one is a polar form. If you still remember, your imaginary number can be represented close in partition, and space also can be represented. How to represent your complex number in polar form? By the magnitude which is r, and the angle which is theta. Right? So now if your theta is 0, if your theta is 0, your if your real part, if your magnitude is 1, it's a unit step. Okay, if it's not, if it's less than 1 or greater than 0, it's your decade. Converge, exponential function is stable. It is clear when your exponential function are diverge. On your imaginary part, this one is like your real part is 0, which is negative is 1. E of 0 is 1. And your theta to be 90 degrees or half pi. Okay, then you see a sine function. You see this is a sine function because your initial condition is 0. Okay, if this one goes to pi, it's a cosine function. Okay, do you see a cosine function? And anything in between is a general cosine sine function with explanation. Okay. So this is over the general cosine sine exponential functions. Represent any position in your polar. So now finally we are able to map. Okay? Last 2 weeks we have reviewed how to map the axis, the region. Now you put this continuous domain to your S domain to your Z domain, right? Basically your left-hand cycle, the left-hand plate represents the area inside the unit domain. And your right-hand side represents outside of the unit domain. Your position here, actually the angle represents the angular here. So forth. So if you close the book, you look at this picture, you are able to explain. It means you achieve at least 80% of what we cover so far. Okay, if you can confidently predict. Okay, from this one to this one. Okay. And this is something we talk about how to map the plan. And today we have talked about how to map. Okay. So this one is we look at the transient response. Because eventually for our design, basically I believe for design control, you only look at two things. One is you look at the long term. Whether your system will become stable or unstable, right? You're talking about the long term. Whether your system stable or unstable. Then you talk about short term, you talk about transient response. Right? You talk about overshoot. You talk about waiting time. You talk about running time. So for the whole control, you only talk about two things. In long term, whether your system will be stable, you actually convert to the value you want. Right? You so-called steady error. Before you talk about steady error, you want to see whether your system is stable. Then the second issue is talking about the transient response. Not only you want your system to be stable, not only you want your system to actually achieve your set point which you want. You also want the setting time to be short. You also want the overshoot to be small. Right? So there are a lot of things you want to discuss. And the control basically is to map your requirement or stability on the transient response into certain mathematical forms. And also a lot of important tools you will see in control. They are dealing with the root locus, they are dealing with where your root is. Because where the root is will give you a certain hint. How is the response? Right? If your root is inside, means your response, your system is stable. But not only tell you about your stability, depending on where it is, it also tell you about the amplitude. It will also tell you something about the frequency. So these are some general guidelines. If your gradient is greater than 1, this one will correspond to a growing signal that will not get error. Okay? So if your output response can be represented and the root is outside of the unit circle, it means your signal of your output won't be decayed, won't be stable, won't be controlled. Okay, so it's unstable. If R equal to 1, that one means your signal will be kept at a certain value at a constant amplitude, which won't die out, but also won't converge. And really pay attention. For this critical case, if you look at the external stability, it will be unstable. Okay? Because if you do the summation of all the impulse responses, because each signal, remember, your output signal is what? If your input is impulse, your output signal is just your transfer function. If everything will be maintained at a constant value of 0, not decade, you sum up what you get. If you sum up infinite time, you sum up the infinite values, infinite constant value what you get. You get unbounded, you get a finite value, you get infinite value. So the critical case for the signal itself will be stable, but the VIBO is non-stable. It's the same case as the trapezoidal case we evaluate just now. Your trapezoidal will be stable at T. Why? Because if you look at the transfer function, it's something over Z minus 1. Is R equal to 1. When R equal to 1, it means your system signal will be maintained as a constant value. Never decay, never convert, never diverge. But if you do the VIBO of the trapezoidal, what do you get? You get infinite. You get unbounded. It's unstable. So the general conclusion is for for any root on the unit circle, either one is not BIBO stable. Is it alright? Is it alright for you? No? One thing very important, I hope you can bear in mind, because a lot of things you can read from the textbook, you can read from the lecture notes. But usually the student always confusing a big mistake, something I think this is the third time I highlight today. The BIBO stability is not talking about a signal. It's a summation of all your impulse output. If you have unit pulse response, you need to sum up every signal, all the signal from the initial to the end. So in this case, because this one I only want to mention 3 times, I don't want to mention 4 times. And believe me, even I mentioned 3 times, later if in the exam comes a question, I will not explain it. Especially those who never pay attention, I'm gonna know. I guarantee you, those students. Okay? So if you go back home, you forget everything, but this is something you must bear in mind. The BIBO stability is not your signal stability. It's not talking about when you're able to infinite value, whether your system give you a finite value. It's a summation of all the outputs. It's not only one. It's not the final one. It's everything add up. Okay? So when your R equal to 1, when you root result in the unit circle, even though you get a finite output at your infinite stage, okay, your final state, you still have a final output, finite output. But if you sum up everything together, you still not on you still feel the BIBO. Okay? The trapezoidal function we studied just now. When your k go to infinite, it's still t. T still a constant value, still a quantum value, right? Still less than infinite. But if you sum up all the time, from 0 to infinite, all the output signal, you get half t, you add up everything together, is unbounded. Then you feel the BIBO condition. Because the BIBO is not talking about the impulse response, whether your system will be stable when you have an impulse response. It's talking about whether your system will be stable, you have any bounded input. For example, the unit step. Unit step is a bounded input. You input unit step to the trapezoidal, you will get infinite when your time goes to infinite. So the system becomes unstable. Okay? But when you're going to evaluate this signal, or output signal. For all those features we're talking about output. Because just now, what the transient response is, what we are talking about? We are talking about output signal. Okay, we are talking about output signal. So if you have a transfer function, you did the evaluation of the root of the Cartesian equation. What actually you did? Actually you did is to evaluate the transfer function which is your hz. Where the z is this. And if you talk about whether this signal will be stable or unstable, you're talking about if I give an impulse signal, whether at the final stage, when my k goes to infinite, my output response will be finite or not. Okay, so this stability has a meaning. So for this stability, when my root is inside the unit circle, what do we mean? We mean our output will be stabilized, right? Or if it's somewhere here, meaning our tooth will be decayed. This decay means what? This decay means my K go to infinite, my FK or my UK will be certain constant value. Okay, when a certain constant value less than infinite or less than infinite, not necessarily be a constant value. So if your signal is, for example, here. If my root is here, what is my response? If my root is here, my response, if my root is here, my response will be something like this. So the output is stable. And this one is basically a value of what? You are evaluating this function. This function is what? You have a uz function. And basically you are talking about your uz function as a transform function. This one only be true if this one is your impulse function. If your impulse, if your input is your impulse, then your output signal will be represented by your transform function. When you evaluate the root loci of your transform function, basically what you get so-called output signal with the input of the impulse. Okay? This stability only means that this stability only means if you have an impulse input, when the time goes to infinite, your output still be 1. But this one does not guarantee if your input change, whether your system still be ordered. Okay, frankly, I was surprised if your signal structure you never mentioned that. Then it means all the signal will have a non-concept of stability. Because when you apply the root loci as well, basically what you have done, you are evaluating your transfer function, right? Because you do the root loci based on the root of your transfer function, right? So what the root of transfer function tells you about? Tells you about your signal output. When the signal output in a signal domain may be like this or like this, what it is? It's a unit pulse response. It does not refer to everything, right? So these are the difference, okay? And the condition is, if this is at a marginally stable, okay? Previously we call marginally stable, right? When we talk about continuous control. Similarly, at the unit circle, if item is on the circle, it's so-called marginally stable internally. But once you put any impulse input, if you sum up, then you are not going to get a bounded. You are not necessary to get a bounded output. Okay? So the marginally stable in your inputs may mean unstable in your VID. Okay? And for the R less than 1, okay? So for responding system is PIVO stable, and we can compute the settling time in steppers. Okay? And you can compute how fast the settling time by the sampling theorem of how many time you need. Okay? Independent of PQR. So for example, if your and the closer it is, the faster your settling time is, and the fewer number of time you need. So for example, if your median is about 0.9, you need about 43 samples. But once you come to 0.4, you will only need about 5 samples. So the root loci in the Z domain can tell you about the stability, can tell you about the transient response. Okay? And this is the final mapping. So means after you get the so-called the transfer function, you evaluate the upon zero, you look at the characteristic equation, then you can do the root type. Then for any location of your root, you can map to a corresponding ratio frequency, damping ratio, as well as the sampling rate.
In summary,
So for example, the number of samples for oscillation of a sinus signal is determined by theta. Okay, if you divide cosine theta k equal to cosine theta k pattern, we find the unit of time. Okay, our hence methods. Okay, if we take the unit of the angle in radian, okay, if we degree, then we try to see. Okay, so in summary, so for today, we basically introduce only one thing, which is input-output response. And for the input-output response, the first issue we will consider is the stability. So for a digital control, or actually for a digital control, when we talk about system stability, we are talking about the input-output response. It means if you have a counter input to your system, you should also have a counter output. And the VIPO can be tested by the summation of all your impulse response. In the continuous domain, it should be the integration of all your impulse response, from the initial time to the infinite. So if you take the summation of all your impulse signals, impulse response output signals, if it's here bounded, then your system is VIPO stable. Okay? We have also reviewed how to think from the differential equation to the Z transform answer. And we also explain again what the relationship between the continuous domain and the linear domain, and also how we can represent all different types of signals. But so far, okay, please pay attention. So far, we only limit to linear systems, which means our signal is all kept excellent to the general explanation function with cosine sign. Okay, we not really present accidentally to any other general. Okay? And only because of cosine sign, second order you will apply. Okay, this applies to the second order. Okay, in connection with cosine sign. We also have some tasks here taken for you to practice. Okay, so 2 years ago, we have done this. They ask you to do the Z transform and actually ask you to map. Okay, 2 years ago, the exam question actually is asked you to think. Okay, and you do this.
John，不要被卡好你。